In this lesson, we'll cover what you need to know to effectively make and report fire behavior observations. We'll also discuss recognizing and describing extreme fire behavior and anticipating changes in fire behavior based on changes in the fire environment. Increasing your skills in these areas will translate to better and safer fireline decision-making for you and the other fireline personnel you work with. Upon completion of this lesson, you should be able to demonstrate the ability to observe and document fire behavior factors, demonstrate the ability to observe, document, and immediately report extreme fire behavior, and demonstrate the ability to recognize changes in fire behavior characteristics that affect safety standards. These objectives tie directly to the tasks from the FEMO-FOBS Position Taskbook. Communicate effectively with supervisor, fire operations staff, and as appropriate, crew members and adjoining resources. Monitor and record fire behavior data throughout the fire management operation. Conduct monitoring and observation operations according to the standard fire orders, watchout situations, and LCES, lookouts, communications, escape routes, and safety zones, principles. First, we'll look at a fire behavior observations form and cover what you need to know to record the necessary fire behavior data. Then, we'll present some examples of extreme fire behavior that constitutes a safety hazard to fireline personnel. We'll finish the lesson with a discussion of critical changes in fire behavior and their impact on lookouts, communications, escape routes, and safety zones. Like all the other forms we've discussed in this course, no single form is standard across all agencies or incidents. This example meets the needs of most fire behavior observation requirements, but check with your incident supervisor to see if a specific form is required for your incident. In this lesson, we'll use the variation of the form used by the wildland fire modules. The fire name, date, observers, time, and location boxes are all specific to the incident and self-explanatory. We covered determining the elevation, aspect, and slope in the unit on mapping. In this section, we'll look at the fire behavior characteristics of spread type, flame length, residence time, and rate of spread. Then, we'll end with primary carrier and fuel model. This section will provide a quick review of the terms as they were covered in S290, with suggestions on how you might measure these factors in the field. The following section on extreme fire behavior will introduce you to some examples of important fire behavior characteristics that you would want to note in the comments column. The first fire characteristic column is spread type. Here, you would note whether the fire in your location is a backing, flanking fire, or head fire. Recall that a backing fire is a fire spreading against the wind or downslope. The defining characteristic of a backing fire is that the angle of the flames with respect to the unburned fuels is 90 degrees or more. In other words, the flames are leaning away from the unburned fuels. A fire spreading on level ground in the absence of wind is also a backing fire. The spread rate and intensity is lowest on the backing portions of a fire. Can you think of why that would be true? A flanking fire spreads at a 90-degree angle to the wind, and the flames are leaning parallel to the unburned fuels. The intensity and rate of spread are greater than that of a backing fire, but less than that of a head fire. The greatest hazard associated with a backing or flanking fire is that a shift in the wind direction could change these fires into head fires. A head fire is a fire spreading with the wind or slope. The defining characteristic of a head fire is that the angle of the flames with respect to the unburned fuels is less than 90 degrees. In other words, the flames are leaning over the unburned fuels. This allows the flames to preheat the unburned fuels and result in greater rates of spread and fireline intensities than in backing or flanking fires. There is rapid heat buildup and potential for spotting, torching, and ember production. Note that almost every fire exhibits combinations of all three of these spread types. In prescribed fire, we often use ignition techniques to utilize one of these types of fire more than another. For instance, we use a strip head ignition pattern to get mostly head fire where higher intensities are desired. In a wildfire, these types of spread are usually found predominantly in specific areas of the fire perimeter. The heel of the fire is usually a backing, and the flanks and the head of the fire usually exhibit flanking and head fire, respectively. Document the type of spread in the location you are observing. Flame length is used as a measure of fireline intensity. Flame length is the distance between the flame tip and the midpoint of the flame depth, at the base of the flame. Flame length is measured along the slant of the flame rather than the vertical height, because it is the length of the flame that is most closely related to fireline intensity and heat production. Remember that flame length is not the same as the flame height and can have a much higher value. Flame length data are usually obtained from visual observations of average flame length, but estimation of flame length is often challenging due to the fluctuating nature of the flames and the difficulty of getting close enough to take an accurate measurement. The accuracy of estimation of flame length can be increased by installing reference points that provide scale. Steel posts with 1-foot sections alternately painted, red and white, or metal flags attached every 3 feet. The choice depends on the expected scale of the flames. Set in the burn area work very well on prescribed fires. These markers can also be used to measure rate of spread. On wildfires, it can be more difficult to access an area before it burns, so look for reference points of known height, such as fence posts and telephone poles. Digital photos taken after the fire has passed can be used to document the flame length, with height measurements of reference points such as trees. Video cameras are also an excellent way to document all aspects of fire behavior. Before we get into our discussion of residence time, let's review the different phases of combustion. This will help you understand the difference between residence time and burnout time. The 4 phases of combustion are as follows. The pre-ignition phase is the preliminary phase of combustion in which fuel elements ahead of the fire are heated, causing fuels to dry. In the flaming phase, combustible gases and vapors rise above the fuels and mix with oxygen. Flaming occurs if they are heated to the ignition point of 800 to 900 degrees Fahrenheit, or if they come into contact with something hot enough to ignite them, such as flames from the fire front. The smoldering phase is the phase of combustion immediately following flaming combustion, and is characterized by smaller, inconsistent flames and larger amounts of smoke than the flaming phase. And the glowing phase is the final phase of combustion following the flaming and smoldering phases. It's characterized by lack of open flame and little smoke production. Residence time is the amount of time that it takes the flaming front of the fire to pass a particular point. The flaming front is that zone of a moving fire where the combustion is primarily flaming. Behind this flaming zone, combustion is primarily glowing or involves the burning out of larger fuels, greater than approximately 3 inches in diameter. Light fuels typically have a shallow flaming front, whereas heavy fuels have a deeper front. Residence time can be estimated from timed observations, digital photography with a timestamp, or a video camera. Residence time is only a measure of the flaming combustion phase of the fire. For monitoring that will later be related to fire effects, an estimate of the total duration of flaming and smoldering combustion of large diameter fuels and duff layers is important. This measure is known as the burnout time. Observations, repeated photography of the same points, repeated video camera images, or a probe-eye infrared detector can be used to determine fuel burnout time. Infrared images can sense higher temperatures caused by continued smoldering or glowing combustion when no visible signs of combustion are present. While it is not important to document the duration of long-term combustion to the exact minute, it is important to note for fire effects or smoke management purposes whether smoldering combustion lasts for only a few minutes, a few hours, or several days. If the burnout time is of more interest to your incident, you can cross out residence time and add burnout time instead. Just be sure the column is clearly marked with the correct title. Rate of spread, often written as ROS, is the relative activity of a fire in extending its horizontal dimensions. It is expressed as rate of increase of the total perimeter of the fire, as rate of forward spread of the fire front, or as rate of increase in area, depending on the intended use of the information. Usually it is expressed in chains or acres per hour for a specific period in the fire's history. The primary factors that will affect rate of spread are wind speed, steepness of slope, and changes in fuel type, grass to timber litter or surface fuels to crown fuels. The head of the fire is the portion of the fire edge spreading most actively. We are most concerned with the forward rate of spread, or spread at the fire's head, as this is generally the most dangerous and difficult type of spread to control. Observations of forward rate of spread should only be taken after the fire has reached a steady state, because this is what the fire behavior models predict. Visual observation and pacing of distances can be used to take rate of spread measurements, particularly on a slow-moving fire. A stopwatch is used to determine how long it takes a fire to cover a specific distance. Rate of spread is calculated from the time-distance relationship. Usually, a fire's forward rate of spread is expressed in chains per hour. Since a chain is equivalent to 66 feet, and an hour is equivalent to 60 minutes, a useful rule of thumb to use in the field is 1 foot per minute equals 1 chain per hour. This estimate will underestimate spread by 10%. Numbered metal tags can be thrown at or near the flaming front. A stopwatch is started when the front crosses a tag, and a second tag is thrown ahead of the fire. When the flaming front crosses the second tag, the stopwatch records the elapsed time. The distance between two tags is measured by pacing or steel tape, and the spread rate calculated. When high spread rates are expected, and/or when it is not safe to be immediately adjacent to the fire, fire behavior can be measured using a grid system installed before the fire. Spacing of markers should be related to the expected rate of forward spread of the fire. Reference point markers can consist of materials such as survey flagging tied to branches or poles painted with bright paint. Times are recorded with a stopwatch or wristwatch as the fire burns past each marker, and rate of spread is determined. If the markers can be marked vertically in 1 foot sections, they will also be useful to estimate flame length as the fire passes them. As with the other fire behavior characteristics, digital photography with timestamps is useful for recording and calculating rate of spread if the distances are known or can be measured pre- or post-fire. The primary carrier of the fire is the fuel type that is mainly supporting the spread of the fire, usually some form of fine fuel such as grass, forest floor litter, or the foliage of shrubs that ignites first when the fire front reaches an area. Observe the surface fire and determine which fine fuels are supporting the movement of the flaming front. You'll find that these primary carriers usually correspond to the 6 fuel groups you learned about in S290. Grass, shrubs, a combination of grass and shrubs, understory foliage in the timber, litter under a timber overstory, or slash from logging activities or blowdown events. Note the primary carrier on the Fire Behavior Observations form. A fuel model is a set of numbers that describe the fuel in terms that the fire behavior prediction models can use. The fuel models presented in this lesson are part of the fire behavior prediction system. In this course and in S290, fuels are discussed in terms of broad fuel groups based on the primary carrier that we just discussed. So for this course, you are expected to only classify fuels into one of the 6 fuel groups: grass, shrub, grass and shrub, timber understory, timber litter, and slash and blowdown. In S390, Introduction to Wildland Fire Behavior Calculations, the fuel groups are broken out further into 53 fuel models, the original 13 described by Anderson, and the newer 40 developed by Scott and Bergen. These fire behavior models and the fire behavior prediction system are covered in detail in S390. Although fuel models were developed as input into the fire spread model, they do provide the wildland firefighter a common way of describing fuels. We don't go into the individual fuel models in S244, but if you already know them or have access to information on which fuel model or models the fire is spreading in, go ahead and fill in the fuel model column of the fire behavior form. Otherwise, the primary carrier is sufficient to identify the general fuel group. Now we've covered each of the specific fire behavior characteristics and fuel model inputs in the form. In the next section, we'll discuss extreme fire behavior, which is something you'll want to note in the comments column and communicate immediately to your fire line supervisor and surrounding line personnel. In this section, we covered the terminology and methods you can use to effectively make and report fire behavior observations. Ensure that you understand your assignment and have the right fire behavior form to meet the needs of the assignment. In the next section, we'll discuss recognizing and describing extreme fire behavior and anticipating changes in fire behavior based on changes in the fire environment. These observations can help you increase your situational awareness, improve the accuracy of fire behavior predictions, and lead to safer decisions on the fire line. The Nwcg definition of extreme fire behavior reads, "Extreme implies a level of fire behavior characteristics that ordinarily precludes methods of direct control action. One or more of the following is usually involved: high rate of spread, prolific crowning and/or spotting, presence of fire whirls, strong convective column. Predictability is difficult because such fires often exercise some degree of influence on their environment and behave erratically, sometimes dangerously. Extreme fire behavior is unpredictable, even by complex fire behavior models. Thus, it makes planning safety mitigations challenging. Careful observation and communication of the conditions that lead to extreme fire behavior are necessary to successfully keep LCES intact during fireline operations. Extreme fire behavior results from combinations of fuel and weather conditions that include abundant available fuels, drought conditions, low relative humidity, strong winds, atmospheric instability, and topography in mountainous areas. Can you see how your responsibilities as a field observer or fire effects monitor contribute to planning and maintaining safe and effective operations? In this section, we'll discuss the characteristics of extreme fire behavior, high rates of spread, crowning, spotting, and fire whirls. In the units on fire weather and smoke observations, we'll cover convective columns and instability. Increasing rates of spread have been a factor in many fatal and near-fatal fire incidents. The primary drivers of rate of spread are wind speed, steepness of slope, and available fine fuels, particularly when wind direction and slope come into alignment. Rates of spread greater than 60 chains per hour, approximately 1 mile per hour, will quickly overcome your ability to escape on foot in steep terrain and smoky conditions. How do these factors relate to some of the fatality fires you have studied? Crowning is a term often used to describe fire behavior, although the term is not formally defined in the fire behavior references. It's a catch-all phrase to describe a number of other more specific fire behavior terms. This sometimes leads to misunderstandings between fireline resources, inaccurately communicating the magnitude and potential of the fire intensity and spread. Understanding the proper use of the terms describing the different types of crown fire will allow you to more accurately and precisely communicate this important aspect of extreme fire behavior. We'll start with the more generic term, crown fire, and then discuss torching or passive crown fire, active crown fire, and running crown fire. Crown fire is a wildland fire that burns forest canopy fuels, the foliage and the fine branchwood of trees and shrubs. So it refers to a fire in leaves or needles that form the crown of the plant. Whether the crown of a tree will ignite is dependent upon the fuel moisture of the foliage, the intensity of the surface fire beneath the tree, the height of the canopy fuels above the surface fuels, and the wind speed. Keep in mind that a crown fire can occur in the foliage of shrubs as well. Torching is a type of crown fire defined as the burning of the foliage of a single tree or a small group of trees from the bottom up. Single tree torching describes a situation in which the fire spreads from the surface into the foliage of a single tree at a time, while group torching describes surface fire moving up multiple closely spaced trees. In torching, the fire does not spread from crown to crown of separate trees, and many of the trees in the area of the fire will not have fire spread to their crowns at all. The spread of the surface fire is reinforced by the torching trees, but the rate of spread will not be increased. Torching is also called passive crown fire. An active crown fire is a crown fire in which the entire fuel complex is involved in flame, but the crowning phase remains dependent on heat released from surface fuel for continued spread. An active crown fire presents a solid wall of flame from the surface through the canopy fuel layers. Flames appear to emanate from the canopy as a whole rather than from individual trees within the canopy. By definition, an active crown fire is dependent upon the heat released from the surface fire to sustain itself. If the surface fire intensity decreases, the fire may cease to spread from crown to crown, dropping down to torching or surface-only fire spread. An independent crown fire is a fire that advances in the tree crowns alone, not requiring any energy from the surface fire to sustain combustion or movement. These crown fires are an extremely rare phenomenon. Few instances of this type of crown fire have been documented. An independent crown fire may also be called a running crown fire. The distinction between passive crown fires, or torching, and active crown fires is critical for accurately communicating the potential hazard. Movement of the fire spread from surface fuels to crown fuels is usually accompanied by a significant increase in the rate of spread. Crown fire often leads to spotting. Spotting is the behavior of a fire producing sparks or embers that are carried by the wind and which start new fires beyond the zone of direct ignition by the main fire. These new fires are called spot fires, and they present some of the most serious control problems in wildland fire. Remember watch-out situation number 16, getting frequent spot fires across line. The flaming or glowing embers thrown off and transported beyond the main fire are called firebrands. They can be transported by winds, convection columns, or fire whirls to start new fires that can compromise anchor points, escape routes, and control objectives. Describing spotting in terms of relative distance can be useful to operations personnel and fire behavior analysts. In short-range spotting, the firebrands land near the main fire and are overrun before they affect the main fire's spread. Long-range spotting occurs in the presence of strong convective columns in conjunction with transport winds or in association with large fire whirls. Spotting distances can be over a mile in these situations, and under the most extreme conditions, spotting distances of several miles have been documented. Long-range spotting can result in new fires, developing undetected far from the main fire, and increase the overall spread of the fire significantly. A fire whirl is a spinning vortex column of ascending hot air and gases rising from the fire and carrying aloft smoke, debris, and flame. Fire whirls range in size from less than 1 foot to over 500 feet in diameter, and large fire whirls can have the wind speed intensity of a small tornado. The ascending, twisting winds can throw firebrands long distances in any direction, and the spinning vortex creates its own directional forces, making its movement through the fire ground erratic and unpredictable. We'll talk more about the atmospheric instability that leads to fire whirls in the fire weather lesson, and we'll discuss the related phenomenon of rotating smoke columns in the smoke observation lesson. In this section, we've discussed examples of extreme fire behavior that can endanger fireline personnel. By definition, these fire behavior phenomena are unpredictable, presenting challenges to maintaining fireline safety standards. Immediately reporting your observations of extreme fire behavior to your supervisor and surrounding resources is critical to safe operations and effective decision-making. In review, watch this video of an engine crew on a wildland fire in California. What examples of extreme fire behavior do you see in this video?
Cyclone of fire, where this fire has generated its own wind. It's sucking up all the oxygen around it and will turn into a tornado. And you will see those firemen actually realize that this is not a safe situation that they are watching, and they will hug the back side of their fire engine just to try to protect themselves against the flame. It's an incredible scene to watch.
You've got to imagine that these guys see a lot in their careers as firefighters, but most of them are saying that they have never seen anything like the fires and the firestorm created over the last few days. This particular crew here is a 3-member crew from Cypress in Orange County up to help out with the fire attack here in the San Bernardino Mountains. This is Engine 17, and as Drew mentioned, these guys are watching these flames, probably somewhat in awe, being that there's very little that they can do to stop them, and this tornado activity spawning from the fire there, and it gets so hot and the winds become so strong here just momentarily that these guys run to take cover on the side of their fire truck and hope that these the flames and the heat will pass them safely. This fire sparked here by an ember, and this particular firefighter running over there to dig the dirt up around it and put it out before it causes an even bigger problem. And as we continue to watch, we'll even hear the fire as it begins to roar through this area, and watch the firefighters as they are forced to take cover.
Yeah, and this was the type of situation back in '96 when, I don't know if you remember those Glendale firemen, where their truck was overcome and those fellows were actually burned. They had fire just like this approaching their vehicle. They tried to get inside and around their vehicle, but the fire came over and consumed it. It was racing up a hillside, and fortunately for these guys, they had flat ground on the other side and little vegetation to grab a hold of. But you can see how they are just hugging the side of their fire engine as that fire, wind-whipped fire just comes right over the top.
And look at the...
Your observations of current fire behavior are useful in providing critical information to fireline personnel and fire behavior analysts. Current fire behavior shows the effects of current fuels, topography, and weather, providing a baseline for planning operations, implementing safety mitigations, and predicting future fire behavior. If nothing changes, neither will the fire behavior, and prediction of fire behavior is easy and straightforward. This is called persistence forecasting by fire behavior analysts. The challenge is to understand how predicted changes in these factors will affect fire behavior. Your ability to observe current fire behavior, assess changing conditions, and then interpret how these changes affect fire behavior can have a significant impact on your safety and those working around you. Many factors can affect fire behavior, but just a few are the dominant drivers of large, sudden changes. Factors such as live fuel moisture and 10-hour fuel moisture do not change rapidly. They are important overall over the course of an incident, but they vary over days rather than minutes. Other factors can change fire behavior over a matter of minutes. So we will focus this section on those changes that can occur over minutes to an hour or so, even though such changes can take place over a longer time period. The biggest changemakers driving fire behavior in this short time are wind, fuel type, and slope. These are the primary factors you should focus on in assessing changing conditions because they are the changes that can cause an immediate threat to firefighter safety. Wind is the biggest changemaker. Shifts in wind direction are common and often sudden. A shift in wind direction can change the slowly backing heel of a fire into a rapidly advancing fire front, particularly in grass fuel types. Are winds steady or shifting near location? Is there a shift in wind direction predicted in today's weather forecast? Are there indicators that upper-level winds are blowing in a different direction than surface winds? Increases in wind speed can rapidly increase rate of spread and flame length. Take a look at this example of rate of spread and flame length changes in a grass fuel model at various wind speeds. Anticipate how rate of spread and flame length might change as your weather conditions change. Is there an increase in wind speed predicted over the fire area today? Have the morning winds been increasing every day at the same time of day? How will these increases in wind speed affect your escape routes and safety zones? Fires experience changes in fuel type as they spread into different fuels, either laterally or vertically. Each broad fuel type, litter, crown, or grass, has a rate of spread range that is distinct from the others. For given conditions of moisture, wind, and slope, litter is the slowest fuel, crown foliage is about 4 times faster than litter, grass is about 3 times to 4 times faster than crown foliage. Observe not only what the fire is presently burning in, but what it is burning toward. Will the fire front burn out of the litter in the understory of a forest onto a grassy slope? How will that change its rate of spread? What fuel type is between you and the fire? Another change in fuel type occurs when the fire transitions from surface fuels to or from the crown fuels above. Vertical spread can occur very rapidly in vertically stacked fuel beds. Such changes can happen very quickly and may be difficult to foresee. Once the fire has become established in the crown fuels, its rate of spread will increase approximately 4 times the rate of the litter fuels as we saw in the last slide. Remember, crown fire can refer to fire spreading in the crowns of a shrub fuel type as well. The transition to active crown fire is difficult to predict, but some practical indicators that an active crown fire may occur include: seasonal drought period prevails, overall drought makes matters worse, recent crown fire on the fire or nearby fires, relative humidity of less than 20% for the western U.S., or less than 35% in the southeastern U.S. Active crown fires occur in Alaska at up to 45% relative humidity. Backing fire produces torching, a dead giveaway that a head fire could become an active crown fire. Fire moving up ladder fuels, and torching in short crown runs. Torching trees are an indicator that a fire is starting to transition from surface fire to crown fire. Pay close attention to these indicators and the other crown fire factors that you have learned in this lesson. If you observed active crown fire yesterday under similar conditions to today, you should expect to see active crown fire today. Slope is the third driver of sudden changes in fire behavior. Slope allows flames to preheat unburned fuels, increasing the rate of spread, particularly when the slope is in alignment with the wind direction. This slide shows some example changes in rate of spread and flame length for different slope percentages in a shrub fuel type. Another type of change related to slope is a change in aspect. The fire may move from a sunny south-facing slope with light fuels to a shadier east slope with heavier fuels. Fuel types often change with aspect, and if the fuels in an area are about to change from being in the shade to being in sunlight, expect an increase in fire behavior. Slope reversals at a ridgetop or in a drainage represent a major change, often in both fuel and wind. These factors can combine to cause a significant change in rate of spread. Some slope reversals are favorable changes, decreasing fire intensity and spread, while some slope reversals are dangerous, with increases in fire intensity and a spread rate of 200 times the previous rate of spread. Slope reversals have played a part in several tragedy fires, including the Man Gulch Fire of 1949, the South Canyon Fire of 1994, and the 30 Mile Fire of 2001. As you are performing your duties and responsibilities as a field observer or fire effects monitor, carefully observe and document what the fire is doing now, but always look ahead to where the fire is going and anticipate what changes will occur as the fire environment changes. In the final section of this lesson, we'll discuss what to consider in maintaining your lookouts, communications, escape routes, and safety zones, or LCES, as these changes affect fire behavior during your operational shift. FOBs and FEMOs are often tasked with performing lookout duties. While you will usually be assigned a location by your supervisor, carefully review the weather and fire behavior forecasts for the day and consider the impact of the predicted changes in conditions at your location. Where does the forecast and fire situation suggest your fire will be moving during the burn period? Will you be able to see the change coming, such as the onset of frontal winds? If spotting is predicted, do you have a view of the areas where spot fires may develop? Can you see into the drainage where a slope reversal could occur? Will you be able to maintain your LCES during these changes? Keep in mind that more than one lookout may be needed to observe and report the expected changes. In addition, clearly communicating the limits of your lookout position in terms of critical changes can help fireline supervisors effectively locate each of their available lookouts. Lookouts, field observers, and fire effects monitors usually take regular observations and document them in logs and forms. Much of the information is of interest on a real-time basis to other fireline personnel and includes critical information such as weather observations and observations of extreme weather or fire behavior. Ensure that you clearly understand what information is to be reported by radio and at what times. Report significant changes, such as approaching thunderstorms, onset of active crown fire, or sudden shifts in wind direction, to your fireline supervisor immediately, and verify that the information was received accurately. Your observation post may put you in an ideal location to act as a human repeater when line of sight, mode, and established radio repeaters are not adequate for reliable communications. Observing, documenting, reporting, and repeating each require a significant amount of undivided attention. If more than one person is required to safely and effectively perform all these responsibilities, make that case to your fireline supervisor. The viability of escape routes can change as conditions and fire behavior change. Make sure you are constantly re-evaluating and anticipating these changes. Will a shift in wind direction affect your ability to use this escape route? Will an increase in wind speed and rate of spread still allow you enough time to use this escape route? Minimum safety zone size is determined by the expected flame lengths and the number of fireline resources, people and equipment, that are anticipated to use the safety zone. Flame lengths that are longer than expected, or reassignment of additional resources during the shift, can change the safety zone size that is required. Keeping fireline supervisors advised of observed rates of spread and flame lengths can assist them in planning for adequate escape routes and safety zones at all times. If changes during the shift make your escape routes or safety zones seem questionable, speak up. Provide the input that will keep you and your coworkers safe in a dynamic fire environment. Let's take a look at how the fire behavior observations you make can be integrated into maintaining LCES during an operational shift. This 8-minute video is a module from the 2010 Fireline Refresher DVD. It asks you to continuously evaluate, is your LCES adequate?
In 1991, Paul Gleason wrote a paper titled LCES and Other Thoughts. Drawing from a long firefighting career that started in 1964 and included working as a hotshot supervisor and district and regional FMO, his paper introduced the concept of lookouts, communications, escape routes, and safety zones as an interconnected system. It has since become the cornerstone for wildland firefighter safety and inspired another generation of firefighters. Brad Mayhew is one of those firefighters and has been analyzing LCES and how we use it.
So LCES, I love LCES, right? In the wildland firefighting profession, just a ton of lists. We got more lists sometimes than we know what to do with, and actually they all have a use and a place for us. But if there's one list that we count on, that we trust, it's LCES. Why? Because those are the 4 key safety measures for avoiding entrapment and burnover in the wildland context. Right? We trust LCES. We trust that if I have my LCES covered, if I have my LCES in place, I'm going to be able, even if this fire, everything goes to hell in a handbasket, I'm going to be able to get out of danger and get to safety, and at least I have my safety measures covered. I know that for the experienced firefighters, that is already intuitive, ingrained. It goes without saying, but I'm telling you, for a lot of folks, there's times where we do LCES without even thinking about fire behavior. So if we could underline this as many times as possible, LCES doesn't make any sense if it's not based on fire behavior. But more than that, LCES has to be based on the fire potential. It has to be based on the worst case fire potential. In other words, I need a safety zone that's going to be adequate. A safety zone is going to do the job if the fire does its worst. This is a key pitfall at LCES, right? Is forgetting about change, right? Fire is dynamic. Fire is constantly changing. Wind is constantly changing. The location of the sun is constantly changing. My location relative to the safety zone is constantly changing. We're in an environment that is constantly changing, constantly dynamic, but it's a very common pitfall to use LCES in a way that's not dynamic. I call it set it and forget it syndrome, right? Where I said, I checked those things off. If the safety zone was there at 10 a.m., I guarantee you that thing is still there at 1600 hours, right? So the question isn't, is it there? The question is it still adequate? Is it still going to be enough? Based on conditions now and how conditions might be changing, is this thing still going to work for me? Dynamic fire behavior means dynamic safety measures. Dynamic fire potential, I need dynamic LCES. I think one of the very useful things about approaching LCES in this way, based on the intent of LCES and based on fire potential, is it gives you a way of defining the components of LCES in a very useful way. Take lookouts, for example. If you ask firefighters what's the definition of a lookout, what does it take to have a good lookout, you're going to get all kinds of answers. Do lookouts have to be on high spots, low spots, see the whole fire, see how much experience, can they have collateral duties? There's all these factors, right? And it becomes pretty tricky to try to nail down exactly what it takes to have a good lookout for this situation and for every situation. Well, with this approach, it gives you a way, I think it gives you a way of doing it. Because what it allows you to do is it allows you to say, look, with this approach to LCES, what is the fundamental intent of a lookout? The fundamental intent of a lookout is someone who's going to see the early warning signs, recognize them, and be able to get the word to me in enough time for me to get to safety. What's the intent of the C in LCES? And one piece of that is when when it's time to pull the trigger and get to the safety zone, I'm confident that there's a line of communication from my lookout directly to me, and that the word's going to get from him or her to me in enough time for me to get to safety. That's one part of communication in LCES. The other piece of it too has to do with making sure that I'm getting and sharing key info about fire potential, about changing conditions, so that as I'm noticing these key indicators, I'm not just keeping them to myself, but I'm making that information available to the folks around me, so that they're using that to update their essay, and they're recognizing the changes as well. How many of us do this, right? Where we go, do I have a way out of here? And you look at that little deer trail and you go, yeah, I got a route, check, right? The real issue is, if this fire starts cooking, if this thing starts doing its worst, is that escape route going to be adequate for me? And in some situations, a 30-second escape route isn't going to be adequate, right? Because a fire can get to you faster than you can get away from it. If I look at the fire potential in my best judgment, right, and I look at my LCS in my best judgment, I make the judgment call that, look, based on what this fire is capable of, each element of my LCS is adequate. If this fire does its worst, I'm going to be able to get myself and my people I'm responsible for, I'm going to be able to get us to safety. What that means is what? I can engage confidently. I'm still going to need to keep updating my essay. I'm still going to want to keep questioning, looking if something's changing. But you can have a 3-hour escape route uphill with all kinds of gnarly stuff. You can have a 3-day escape route, as long as that escape route is adequate based on the worst case fire behavior. If it's adequate, it's adequate. It's a judgment call. Human beings are not going to make perfect judgments, right? But there's no substitute for our subjective human judgment. What's the definition of a safety zone? How big does it need to be? Where does it need to be located? I don't know how you define that objectively. The only way to define a safety zone has to involve some element of human judgment, right? It is a judgment call to some degree. So let's define what that means. The issue with the safety zone has to be this: based on what this fire is capable of, am I confident that this spot is going to be adequate, that we're going to be all right in there if this fire does what it's actually capable of doing today? It's not something that I do for OSHA. It's not something I do for the chiefs. It's not something for the guys in City Hall or the state capitol or even in Washington. We don't do LCES for them, right? We do LCES for us. LCES is for me, to avoid me getting burned and the other people that are with me. It's for us to avoid getting burned. That's it. That's all I have to say.
Can you see how your observations and communications as a FOBS or FEMO are related to maintaining fireline safety? In this lesson, we've covered what you need to know to observe and report fire behavior, including extreme fire behavior conditions, and how changes in the fire environment can affect fire behavior and LCES. When you are performing your duties as a FEMO or FOBS, continually reassess your situational awareness based on what you have learned in this lesson and the lesson on weather observations. Ask yourself the following questions, and discuss these questions with others on your assignment. Weather. Do you have a recent weather forecast? What changes in weather are predicted? Fuels. Is the fire burning toward a change in fuel type? Are there indicators that the fire may transition into an active crown fire? Topography. Is the fire burning toward a change in slope steepness or aspect? Is the fire burning toward a potential slope reversal, such as a ridgetop or drainage? Fire behavior and operations. How will predicted changes in the fire environment affect fire behavior? What will a predicted change in flame length, rate of spread, fuel type, spread direction, wind speed and direction, or fuel moisture mean in terms of your LCES? What would it mean in terms of meeting the management objectives of the incident? Will your protection tactics still be effective? Will the fire effects still be within the desirable range? Do you have clear instructions on what to do if tactics or assignments need to be modified? Carefully and accurately observing fire behavior and anticipating changes will increase your situational awareness and prepare you and those working around you to react swiftly and safely to the dynamic conditions inherent in the wildland fire environment.